You guys can let me know if there's any issues or anything. My Zoom has been flaky of late, but I'll try to make sure that it's I can keep the information flowing here. I think we'll do okay. So it is 6 o'clock. We'll go ahead and get rolling. I know a lot of the guys on the board are going to not be able to make it tonight. Just a number of things have come up, and we'll get a few people coming in too. Tim's not going to. He's just going to be here audio wise. He's going to connect, and then I just got a message from Kevin, our vice president. Kevin is a very good organist, and he is under the gun the 2 weeks before Easter all the time, and so he has to travel out and tune in Oregon somewhere on the Front Range of Colorado tonight. And so we'll let him do his job. That's a pretty unique job that he's got, and he does a good job at it. But I'll go ahead and throw up let me see if I can get this to work. And so you should see the screen with a quick agenda on it. We'll go through the officers' reports real fast. Not a lot to report. We'll give you a quick update on how we did in March with our event at the beginning of this month and what we're still going through right now. Also, a quick reminder to anybody out there that hasn't renewed, please do that. But we do want to get to Dr. Jeff Sherwood tonight. He's been kind enough to join us tonight. He's traveling the country and under some difficult circumstances, but he was able to sneak in and visit with us this evening, which is really great. So we'll get to him as soon as we can. And if there's any other new business that we need to take a look at, please let me know. Our next meeting, just to throw that out there, will be in 5 weeks on April 27th. That's the fourth Thursday of the month. So that's sort of the plan. Does anybody have anything they want to throw into this agenda, or is there anything different that we need to look at? Okay, so let me go ahead and get rolling. Darren is not here this evening. He had his last chemotherapy treatment this last week, and he knew that he would be probably down for the count on this last one. He is recovering from an intestinal cancer and had surgery at the beginning of February, and was able to come and recover and make it to our March event, which was great. And he's doing quite well. So we're wishing the best for Darren, but he has a good excuse for not having minutes. Mark is here tonight, maybe? No, he's been pretty busy with his work too, and he stays late at work. He has been able to help us the last 3 weeks though with our FMT, and so he'll be there again next week on Wednesday night, and we'll talk about that briefly. Tim is someplace, I'm not sure where he is, but he said he'd rather not have to connect. I think I've got that right, Tim. We'll let the big T stay up on the screen. As far as the treasury report, he does have the February update posted. We've had some deposits come in from renewals for club membership. We've also started to process all the QSL card requests for our the week that we operated, and so we've had some money come in there. I'm about a third of the way through all of those. So we've got well over 100 requests in the mail. When I opened up the mailbox, there were 70 mails jammed in that little box. Like I said, Kevin's not much to update. I'll just update with a quick review of what we went through at the beginning of the month. We had 2 talks at the museum. Glenn Nelson from the WWV station North gave a great history presentation on WWV and frequency measurement. We had a good crowd there, folks, local hams. We had also folks come up from NIST Boulder. The program was recorded and it was broadcast. Some of you were able to see it. We did have a few audio glitches in there as well, but I think the program went very well. And we don't have that recording posted on online yet. The Northern Colorado Amateur Radio Club was kind enough to help us get that up, and so I'm working with them to get that finally posted. The other half of that evening was also the ham side presentation, and I thought it went very well as well. So we had Dr. Kazan, Rachel Bodecker, and Aiden Monterre, all from originally from Case Western, and Aiden, she now works down at the NIST Boulder. On Saturday or on Friday, we had these great tours of NIST, and I don't know if this will show up or not. It looks like it might. And I'm going to go through these real as fast as I can. Hopefully they flip for us, but oops, maybe not. Maybe I won't do this. But we had just a fantastic tour all the way through the facilities down in Boulder. Just the neatest thing to see all the the helium masers and the different clocks that are all networked together. They have names for all of them. This is an experimental shelter that a Brazilian scientist is working on cooling a clock. And we had some of the best minds down there. Vlad was there, Greg, Mike, I can't remember her name. Mike is, I think, still on here.
LaDan.
LaDan, thank you. So the three of them led these tours. They were great. They answered all of our questions. We got to see so much in the place, and just fantastic. Very neat to be in the old part of the NIST building, the original 1950s building, and then to walk into the brand new buildings that have been added on. We got to see the fountain clocks, which were kind of cool. This is the F3, and there it is doing its thing. The light on over here, so you can see that the laser's working. This is Tim, our treasurer, on the tour, and he's taking a photo of this really interesting benchmark that had just been put in the floor a couple of days before we got there. And I just think it's kind of cool that it matters that you have to make and measure the distance of the clock off the floor because time runs at a different rate when you're 30 centimeters farther from the center of the earth. I think that's neat. Really great networking of all the equipment to be able to keep everything up and operational. It's impressive. This is the F1 clock, one of their first original fountains that is, at some point they think, I think the comment was they took the heart out of it, so they're gonna have to give it a new name. But essentially it was the original fountain that they had worked on. We also had a great tour of WWV, Matt Deutsch and his team up there, amazing. So we had a good crew. Checking it all out, we got to see WWVB and the control board for that. Amazing to sit there and see 50 kilowatts and 800 watts coming back in reflected power. That would be tough. Beautiful views of the Helix house. We got to go in. I like the sign on the door, don't go in here. We all committed a federal offense that day. It was fun. And Matt showed us around. We took a look inside, and what you see are these massive variometers and coils. And it's a really kind of a neat thing. And there's a lot of RF in the air, enough to light up the light bulbs. So it's kind of fun. The station, of course, of WWV. This is some of the QSL cards. I will point out that Case Western got one up when they were there 3 years ago. And so there it is. It's still up on the board. In fact, some of these QSL cards are in the photos from the 1960s. It's pretty fun to look at that. Rachel Bodecker, who is working on the GRAPE project and doing her doctoral from Case, standing in front of the 10 megahertz, which is kind of cool. Bill Yates did a great job. He does an amazing tour. And this is in the clock, or the clock room, I think is what it's, the code generator room. And so this is where you hear the clock and the ticking and the LEDs swinging across. The antenna's heading out to the field. We had a really nice afternoon, stormy, and got some impressive pictures of the antennas. And then Saturday, we had the great event at the museum. Rocky Mountain Ham came and helped us get a nice antenna up in the air, drew some attention, and a good vertical that we had. Mark, our communications director, set up an amazing station with the Flex Radio, PGXL, and TGXL. There's Darren in the background helping out with this as well. And we had the Shy-Y Club there. RJ and Doug, two of our members, came down and did a quick demo on satellites and a talk on satellites. The Estes Valley Amateur Radio Club came. We had the Northern Colorado and R1D1 there. We also had the Boulder Amateur Radio Club did amateur TV. There's Kevin and John K-Bone, two of our members of the club, talking to Bill over here, and I can't remember Bill's call off the top of my head. But anyhow, the ham side group, Mark again. And we had this wonderful theater that we were in. This is down here in the lower corner is Larry Olson giving a talk about their ARC presentation. And you've got this giant screen up here, and it's very difficult to work with because you can't see it when you're presenting. So it's kind of funny. And of course, Doug gave a great presentation on satellite. We had a parks presentation from Jeremy. It was all really good and a quick summary. And that's what we did for that fun weekend. And I know some of you guys were there. Some of the folks made it. Some of the people did not. But it was, I think, a very successful event. And then we went right on into the 100th frequency celebration special event station. Gary and Fred, you want to give a quick update, and then we'll move on.
Fred, you did about 95% of the work, so why don't you take it away?
Thank you. I'm not sure about that. The work was done by the operators. We just kind of facilitated it. We started the special event station at 0000 hours on March 6th, which was right at the end of the ARRL CQ worldwide the sideband contest. And we ran for 7 days through the following Sunday. Just taking a quick look, and these are unofficial numbers. Logs are being tallied as we speak, but we had 9 operators. We had around 106 operating hours during the week and around 21 or over 2,100 contacts. So we're hoping that Dave's mailbox will get stuffed a couple more times. I did quite a bit of phone, and I enjoy that part of it because you get to hear a lot of stories from people. You know, we try not to run it like a contest. We try to run it like a special event station. So you spend time with the operators that want to talk. But I'll have to say I probably had a pileup going most of the time that I was on sideband, and tried to give some plugs for the club. Of course, for WWV, explained why we were on the air. And I think we'll probably have quite a few QSL requests. We have a unique card, thanks to what Dave did for this event. And it's a ton of fun. Hopefully we'll do more of these special events. I would really encourage all the operators to get on and run as much as you can, because you'll hear great stories. You know, people who said that WWV's played a huge part in their life. Maybe back when they were in grade school or high school, they started listening, and they tune their radios now, and it just goes on and on. It's a hoot to run it. So I didn't get on until later in the week. Didn't make as many contacts as I wanted to, but we had fun. Gary?
Yeah, I'll second that, Fred. It was a lot of fun. I operated almost, I think, exclusively CW. I did operate a couple of short contests, one of which the exchange was a signal report and an operator's name and QTH. It was no problem sending Ohio, but in one of the contests, I tried to be the smart aleck and I sent my name as NIST, and that threw a lot of people off. I mean, the contesters should be hotshot operators. They should be able to copy anything. But when I would send NIST, I'd sometimes get question marks back. So that was my fun part.
Question marks. That's funny. Well, thanks guys for putting that together. It's always good to get out there. Some of the QSL cards I've already gotten. Somebody sent me a copy of their signal report they had back in 1967, and they got a QSL card from WWV here in Fort Collins. And we've seen those come up, and we should get some of those old cards up on the website so people can see what they look like. But it was the card that they were putting out in 1967. They put that same card out for almost 50 years from Fort Collins. And so I still think Fort Collins should get another QSL card. I think they could do that. Anyhow, we had the frequency measurement practices the first 3 Wednesdays of this month. Well, the second, third, and fourth Wednesday. The last Wednesday of the month next week, we're going to do another practice. You can get to that by going to our website and just clicking on the FMT, and there's some instructions there. And we did broadcast last night from both Ohio and from Colorado. Not everybody could hear each other, which is, a reality of the FMTs, but I thought it was a good practice. We're going to do the same thing again next week. We'll probably try to, do it closer to the format that they do for the FMT. Just to, we'll talk about it a little bit online too. So if you're interested there's no reason you couldn't get in and join in with us. So it'd be kind of fun if you could do that. So what I would like to do right now is to go ahead. I think I didn't want to drag it out too long. I wanted to give time to Jeff from NIST in Boulder. He's still on, and he should be able to share anything that he might be able to do from his laptop. But I want to give you a quick background. Dr. Jeff Sherman received his PhD in physics from the University of Washington, and he came to NIST in 2009 to work on the optical atomic frequency references and laser stabilization. And that's a real key part of all of these fountain clocks. His tenure at NIST has included work on the NIST's Internet Time Service and the ensemble timescale of the atomic clocks, comprising the official source of time and frequency signals, otherwise known as UTC, and in quotation marks, NIST. And the other one is the Naval Observatory. The other one for the US is the Naval Observatory. And so we're going to go ahead and hand it over to Jeff. Jeff, are you there? He's there.
Yes, this is a mic check and a camera check.
Look good, Jeff.
Everyone receiving. All right, I'll try the screen share check, and that would be enough checks.
Okay, it's all yours.
Let's see. Yeah, it's not clear it's going to work. Let's see if it's a permissioning issue that I can fix real quick. I'll have to quit and reopen, I think. I'll join
Okay.
very quickly.
No worries. I think I've got mine set properly here at this end, so.
Hey, Dave, while you're
I'm going to
waiting.
test the room. Go ahead, Fred.
Okay, I just wanted to give special mention for our operating event to Dave, KN4SON, who operated 47 hours
Oh my
during the
God.
week, made 608 digital contacts. So there's a shout out for you.
He did that the year before too. You got it last year, and then the year before he got that. So good job. Thanks, Fred. Jeff, give it a shot.
All right, sorry for the computer snafu.
No.
Let's try again. You
There you
should
are.
see the whole screen, and I'll attempt to share the screen, but anything can happen. All right. Fantastic. Let me know if the screen isn't showing up.
I think it looks great.
All right.
Good.
Well, again, thanks for inviting me, and I'm glad, Dave, that you showed what you saw on the tour. I feel bad I wasn't able to make the tour, and so this is good penance. And I hope if some of you are on it and you had more questions, you'd be able to ask today. My goals are really to do three things that are all impossible to cram together. One is to give a very general overview, but not just general. You're all technical folks, so I wanted to tell you at least something in some detail, but then also reserve some time for questions. You probably do have some very good questions. So we're going to try to take from a buffet of those three dishes. Let's see. If I were to describe the time and frequency division at NIST, this is sort of my view of it, that the kernel of the work begins in research and development of novel techniques, which these days really means ultra-stable oscillators. Specifically, that means lasers disciplined. Their frequency can be disciplined to stable macroscopic objects, special glasses that hold their shape to within the width of a proton averaged over a large mirror surface and averaged over about a second. And it transfers that length stability to the laser's frequency stability such that these oscillators have coherence lengths of about here to the moon, or about 1 hertz of line width on a 10 to the 15 hertz, hundreds of terahertz kind of oscillator. So they're just sort of incredible realizations of coherent oscillators. And the bedrock of these oscillators is then used to build frequency references out of atoms. And these form the core primary references for which we reference the commercial atomic clocks that continuously measure time, and an ensemble of those clocks is what we call UTC NIST, our broadcast official timescale. And sort of that, in my view, forms the core of the division's job. That's sort of our key mandate. But the applications from that point are many and varied. And in particular, we try and broadcast and distribute the time in as many ways as possible for free if we can. And the most popular for free methods are the radio signals and the internet time service, which is probably the most popular used service from any national meteorological lab in the country. The request rate is currently 100 billion with a B requests per day. Each individual server probably receives 400,000 requests per second, essentially saturating the network stack of FreeBSD operating system. When it's not possible to distribute the signal free, we try and make services where we recover just the bare cost for the service. And there are various other agencies and industry customers who need time at the microsecond level or tens of nanosecond level. And the highest resolution we can offer is really only used to connect to other national meteorological labs using geostationary satellite transfer. But we're aiming to make that service generally available also now that there's a demand. This is something I'll mention a bit later. In addition to providing these sort of live signals, there's another way we touch industry. Clocks, it turns out, can be either part of or themselves can be turned into very interesting sensors. And to the extent that they can be made portable or use small technology, they can end up in handheld or rack-mounted devices. And so there's a big technology transfer program to try and take the laboratory instrumentation and move it out. So maybe the one you're most familiar with is the so-called chip-scale atomic clock. Commercial versions of that are now being produced, I think, by about 4 companies, but it was invented at NIST. And those same miniature atomic vapor cells can be turned on their head into magnetic sensors. And so that's a technology being incubated right now. And the state of the art also has applications. They're a bit further from usual industry, but coherent transfer of that ultra-stable laser light effectively means keeping relative time at the femtosecond level. If you think about what one wavelength of an optical wave represents in time passing you, it's about a femtosecond. And if you can stabilize a relative path length between 2 stations and share coherent light between them, it effectively means transferring phase at femtoseconds. And so there's burgeoning applications in quantum information transfer and processing at low speed radar. Might depend on oscillators kept stable like this, and things like radio telescopes that use a technique called very long baseline interferometry could immediately make use of this sort of technology. It's not a time code like time of the day, but it carries coherent phase at an exquisite level between places. So in a nutshell, this is sort of what the division's involved in, at least from my perspective. As I said, the most popular way we broadcast time is over the internet. And if you'd like an audience participation moment, you can press escape or something and everyone launch a web browser and type time.gov. And this does not directly use the 100 billion requests per second NTP service, but behind the hood, this website does use NTP to synchronize itself. And this website also, I point a red arrow on this plot to an interesting part of the display, and it shows how calibrated your device is. And that depends on a lot of things, your operating system, how it's been configured to get the time. And the idea is that there's packet exchange between this website and your device. And the packet exchange accomplishes a delay measurement. And that's how the website will be able to tell you personally how close or accurate your device is. I wouldn't worry if you're a fraction of a second off. That's sort of typical for desktop computer operating systems. You have to work really hard to do much better. And the substrate of the public internet is not really appropriate for having accurate time transfer at, say, the 10 or 1 millisecond level. It's quite difficult to even tell what the errors are. The paths are so noisy. But if you'd like, in the chat, you can, if you think you have the lowest absolute offset, go ahead and type it in, and we'll see if anybody clearly is the winner. So the broadest possible motivation for why we do all this stuff, I think, is that nature, no matter where you look, gives us a sufficiently good time reference or phase reference. There just is no such thing. And if you name one, I'll tell you that the way it's not sufficiently universal or available all the time or stable or practical to use. So instead, nature does seem to give us exquisite rate references. And if we follow this recipe where we decide to count periodic occurrences out of a physical oscillator, whose rate we periodically reference to these exquisite rate references that nature gives us, then this is the best recipe we have, owing to the fact that there isn't a nature-made phase reference out there in the universe that we know of. And this has been an incredibly good recipe. It doesn't have to involve atoms and quartz oscillators. The same recipe exists when, for example, the oscillator could be a pendulum, and the rate reference might as well be an astronomical object in the sky, even the sun. And that same recipe just gets better and better when the technological components are improved. Around the time we abandoned the best of the pendulums, we realized that we could build mechanical oscillators that were more stable in rate than the rotation rate of the Earth. The Earth is kind of a lousy oscillator. Its size changes every time there's an earthquake. The tides is a frictional source that over the long term will slow Earth's rotation rate down. There's all sorts of wobbles and wiggles. And say after about the 1920s, we had realized pendula and quartz crystal oscillators that were better, more stable than the Earth's rotation rate. And so we're sort of off to the races. In this plot, it looks like an exponential, but then you realize that it's already on a logarithmic axis. It's a double exponential of rate of improvement. And we're sort of hanging on by our bare teeth, really. Why are atoms so fantastic as rate references? Well, the physical basis really has three facts in it that make it so. It's currently our belief that all atoms of a given element or isotope are fundamentally identical. They're indistinguishable. It's not like they run down. They don't have batteries that need changing, and they're not different in Boulder than they are in Paris. It's a testable assertion, and it will be very interesting if we discover that this is not true. But to the extent that we have tried testing it, it seems like a true assertion. So they're made to exact tolerances, unlike quartz crystal oscillators or pendula. Number two, the internal degrees of freedom of the atom, by which I mean the arrangement of charges, can only exist in discrete configurations. That's the quantum in quantum mechanics. And every difference in energy between these configurations is related to a rate by Planck's constant, which we also think is a constant in time. It's invariant. Also a testable assertion, and has proven true to exacting precision. And finally, atoms are dielectric. They're like little antennas. You can move the charges around by impinging electric fields on them. And likewise, when the charges move, they emit like an antenna electromagnetic field. So that there's an interaction handle on the atom where you can get rate information in and out. And really, this leads to both an advantage and a disadvantage. The disadvantage is the atoms are sensitive to their environment. They're sensitive to temperature in this way because black body radiation shines on the electrons and jiggles them around. But on the other hand, this is our handle to get inside, manipulate, and measure the rate information inside of the atom. So it's a double-edged sword, but it's one that's unavoidable. The current primary realization of frequency is based on a lowest lying microwave transition in the cesium atom. It's not fundamental that cesium was chosen. There's a recipe for every single transition and every single atom, but there are engineering advantages for several of the atoms that are studied. And what I show here is an apparatus that is sort of the endpoint of maybe 40 years of engineering to try and suppress mainly the Doppler effect of how do you suppress the relative motion between a laboratory microwave field, which you think of as stationary, and moving atoms, which you're not allowed to hold on to because doing so would perturb them too much. And as you're probably aware, the fountain exists based on laser cooling. The atoms are cooled by lasers to about a microkelvin or below absolute temperature. That's really to control their expansion as they're then sent on a ballistic trajectory up and then down. They're only moving at meter per second sort of speeds, so the Doppler effect is immediately suppressed. And then there's very clever design about how the microwave fields are introduced to be very symmetric around potentially moving atoms to further suppress the Doppler effect. You end up with a spectroscopic signal shown there on the bottom right, say, where in just about 1 second of measurement, you can resolve the relative frequency difference between your synthesized microwave at 9.1 gigahertz and the atom's idea of 9.1 gigahertz, which is the reference. And essentially, this curve shown on the bottom right is stationary such that it can be averaged for millions of seconds and split that line by a factor of 1,000,000 to decide what the center point is. Doing that effectively disciplines the microwaves to have an average frequency that's the same as the average cesium frequency that you've traversed through your apparatus. It should go without saying that the time is sort of a fundamental quantity in all of metrology. And the SI system of units has recently been redefined to make this even a truer statement. I don't want to get into every aspect, but I'll cite one example. Another audience participation moment, number 2. Does anyone know before the recent SI change how current was defined, the ampere? And if you know, unmute and tell everyone. I'll give you 4 seconds.
Well, it's a certain number of electrons passing any point in 1 second.
Not true.
63.
It's not true. That is not how it was defined. If you look, it was previously defined in terms of the force between 2 infinitely long wires it's the current needed to create a certain force of, something like 10 to the minus 7 newtons.
Yeah, Coulomb's force.
Between 2 wires separated by 1 meter. It sounds like a crazy definition to our modern perspective because I'm sorry, the gentleman who spoke, that in fact is the way it's defined now, a count of electric fundamental charges in a certain period of time and time interval given by a quantum mechanical rate reference. That's our current, that sounds like a great definition to our current way of thinking, but back then it was the most practically realizable technique. And what really mattered was electromotive forces. You really did want to move things with electromagnetic field, so it made sense. But you can imagine how such an arrangement of trying to measure a small force between 2 wires limited the practical realization. Just the uncertainty in the construction of that arrangement would limit the realization of the unit. And so there's been this progress to try and tie our units to things we believe are constants of nature and given to us by nature. And okay, so I've given one example, but there are several stories just like this for almost all the units. Practically, the most significant use of timing at the nanosecond sort of level, nobody needs to be on time for their work from home Zoom meetings at the nanosecond level, but global positioning systems really take the cake in terms of high dollar value and a direct application where 100 nanoseconds isn't good enough really for what people want to do with GPS. And I'm sure you know how it works, so I won't belabor the point. But if you're curious to know more, NIST commissioned a study a few years ago, linked below, estimating what the economic damages would be from a temporary loss of GNSS. There's just so much economic activity tied to it directly and indirectly. It's sort of mind-boggling. And really, that's just it. The rest is sort of engineering. As I mentioned, you can craft a frequency reference or clock out of several atomic species. This is a concept that will be true generally across quantum mechanical systems. It's just that certain particular atoms and arrangements are practical from an engineering standpoint, and the rest is a function of how much size, weight, power, and money you have to throw at the problem. And I show below a kind of nice review article of all the technologies that are on the market now. Just to review how the system of international timekeeping works, there are about 400 commercial atomic clocks that are run continuously and whose data is reported to an agency in France called the Bureau of Weights and Measures, or BIPM, which is the French acronym. And those clocks are not assumed to be accurate. They come with parts in 10 to the 12 sort of frequency offsets. The hydrogen masers in particular have drift, but they are expected to run without cycle slips essentially forever when you turn them on until the day they die, which could be a decade. In contrast, the primary and secondary frequency references of the world, there are far fewer of them, and these are the cesium fountains and new optical atomic references I'll talk a little more about. What they do is measure the rate, not time, but rate of the international timescale EAL, the free-running atomic timescale, and publish calibration measurements monthly such that the free-running ensemble of atomic clocks has its rate adjusted to make what's called TAI, or International Atomic Time, which is the same thing as UTC, except with the insertion or deletion of an integer number of leap seconds. I don't want to talk too much about leap seconds, but they're what you do to keep the atomic sense of time roughly corresponding to the astronomical sense of time, like the sun is overhead Greenwich at noon, to within plus or minus 0.9 seconds is the current arrangement. And leap seconds traditionally have been added about one every 1.5 or 2 years. But if you've read the news recently, we're in a bit of a dry spell since the dot-com boom. There have been far fewer than average. And the signs are pointing to Earth's rate speeding up such that there may be a negative leap second in about 6 years. Stay tuned. The worldwide ensemble of atomic clocks consists of mostly the 5071A high-performance cesium beam standard, shown here in orange, a growing number of hydrogen masers, and a few prototype clocks shown here in green. On the other hand, the hydrogen masers own 90% of the weight. There was an administrative change made, I forget when, but maybe in 2014. Oh, it's shown there at the top in civil year, yes, where a decision was made by BIPM to allow the hydrogen masers to capture more weight. It's essentially a compromise. The hydrogen masers drift, so to give them more weight, you have to discount that drift per maser clock. So there's a more sophisticated model that discounts the deterministic effect of each clock. And the reason they did this is because masers cost a lot of money, and those laboratories that own a lot of masers wanted to see them have more weight in the timescale. So politics never leaves any scientific endeavor. How we do it at NIST is, as you've seen in the tour, we have about 20 hydrogen masers and cesium beam atomic clocks that comprise our own free-running atomic timescale. We have a nickname for it, AT1, and we steer the rate of AT1 infrequently, a little bit like how EAL gets its frequency steering to make TAI, but we do it to generate UTC NIST, which is our best forecast of what UTC is at the present moment. UTC does not exist at any place in real time, even at the BIPM, which creates it. It is a so-called post-computed timescale, which means it exists as data of UTC NIST versus UTC a month ago. That's how we learn about it. You've already seen pictures of this. There are clocks distributed in environmental control chambers. They all get their phase measured at these fancy, essentially sine wave phase measurement machines. We drive several synthesizers to steer the output of particular clocks into realizations of UTC. We do it 4 times so that we have 3 backups sort of two realizations in two different buildings. And the Fort Collins radio station has their own ensemble of cesium beams, two different steering synthesizers, so they have two possible steered outputs to use as their reference. And then it leaves the building from various ways, the internet time service, or what's shown there is a KU band antenna pointed to a satellite hovering above Brazil. It has a down beam in North America and a down beam in Europe, and we've leased the transponder bandwidth to get across. This is how we transfer UTC NIST to Europe. This is about how well we do. These are the reports that are published monthly in blue. That's the official data. And weekly in orange, which is unofficial and noisier. So you'll get in trouble if you try and follow the orange curve strictly. And if you want to know what it's like to work at NIST, the job boils down to trying to make this curve both small in magnitude and smooth, which means not following every bit of noise, because the noise in the time transfer itself is not insignificant. This is a plot of the same sort of data, but as a statistical measure we call time deviation. It essentially describes the predictability of a time comparison as a function of averaging interval. And the black data starts at a day because that's the shortest interval over which BIPM measures. What's shown in colored lines are various models for single clocks. So you could see that UTC NIST does better than any single clock, owing both to the ensembling that we do, the sort of averaging of multiple clocks, and the fact that we're steering it at about the weekly or monthly timescale to agree with the rest of the world. Okay, so that's the broad overview. I wanted to give you some meaty specifics, and I wanted to pick some current events, just things that are going on that might be interesting to an audience like this. So I won't be able to say too much about them, but this is what I hope to talk about and finish up. The story of the last 2 decades has been that optical frequency references are now evaluatable at accuracies below the definition of the SI second or its inverse, the Hertz, which is puzzling. How could that be? Well, it's true. If you compare a realization of an optical clock against a cesium fountain, you'll get the uncertainty of the cesium fountain. But when you compare optical clocks against each other, they show relative instabilities and uncertainties that are orders of magnitude better than the part in 10 to the 16 or so that the cesium fountains exhibit. So it's an uncomfortable position to be in as a metrologist, because we are now working with devices which we believe are more accurate than the standard of time itself. So everyone's curious about, when are we going to redefine the SI second? And we're sort of in the middle of it, trying to decide which of the optical species is best, which is not merely a technical question. The best clock in the world is still no good if only one laboratory runs it. If you're going to pick a standard, it has to be one that multiple labs have had success with. So it's a fun, interesting process. There are 2 broadly candidates for the types of technology. And the story for these clocks is really the same as the fountain. You need to remove residual Doppler effects from the atoms, except in these optical clock techniques, you can cleverly hold the atoms essentially at rest with one technique or another. And the real key is that you have to hold them in a way. It's a strong perturbation because you're holding on to it, but it's a tailored perturbation that affects 2 states of the atom identically. And those 2 states are the ones bridged by the optical photon. So on the left is a electromechanical technique of trapping a charged atom called an ion, essentially because the charge degree of freedom is totally separate from the internal arrangement of the electron degree of freedom. That's the key to that technique. And it's sort of kryptonite, if you like, is that there are still motional residual effects. In fact, this is a radio frequency trap, and the ion has some residual driven motion at that frequency. It turns out mostly that motion resolves as sidebands put far away from the carrier, which in our case is that clock transition. But at second order, there are relativistic Doppler shifts that come to haunt you, and you have to characterize the motion very carefully. On the right is shown a cartoon picture of a trap of neutral atoms. Atoms seek high magnitude of infrared standing wave laser field for the same reason that dust likes to seek bright light sources. Matter is dielectric, and so that's one of their properties, is it will seek the high field. And in this case, the frequency and the power of the trapping laser light made into a standing wave is tuned just so, such that two of the states are perturbed exactly the same amount. And that can only be done so well in practice. So in fact, that perturbing light is the kryptonite, the sort of hard part of that sort of realization. This is a long exposure photograph of the ytterbium optical lattice trap at NIST. This is involving neutral atoms that are deep inside the vacuum chamber. You can see illuminated by some of the bright lights around. We took this picture by, it was a sort of a 30-second exposure, and then you wave around an index card where you know there are laser beams. You should definitely see a blue one, a green one, a red one, and a yellow one. The blue and the green are involved in the laser cooling of the atoms from a vapor phase, reducing their kinetic energy such that they have a temperature of about 2 microkelvin or so above absolute zero. The red laser beam is the one that is retro-reflected on itself to make a standing wave of light. That's the lattice of regular trapping sites. The atoms are cold enough that they fall into those sites and get trapped. And the yellow light is where the oscillation of the clock is kept. And the idea is shown there on the right. What it is a scanning experiment where the laser frequency is tuned like 1/10 of a hertz at a time, which already implies almost magical degree of technological sophistication. But never mind, the laser is tuned by 1/10 of a hertz at a time, and it traces out the atomic response as this wonderful coherent response with a line width that's limited by the inverse of the exposure time. And if you stare at it, you realize the signal to noise is, I don't know, about 10 or 20 in one shot, lasting about 1 second. So the name of the game is just parking the laser right in the center of that fringe. And how well can you keep it there? And if you keep it there well, then over time you get to inherit the average frequency of the yellow light will follow the average frequency of the atoms. And this holds true below parts in 10 to the 18. They're now running this clock with precisions in the 10 to the minus 19 relative to other optical clocks. This is a current event. So this apparatus, the one in the photograph, just ran for 2 months to calibrate the SI second. And that data was shipped off and published in the BIPM's monthly publication of this sort of thing called Circular T. You could go online now and find the distillation of this data, but I'll show you the internal stuff. So what I'm showing you is the month of February, and the ytterbium clock ran for 6 days. That's the 6 clumps of points. Every point represents an average over 12-minute intervals. That 12 minutes happens to be the rate at which we measure the masers officially. And what's plotted in the black line is the difference between UTC NIST, our broadcast scale, and our private free-running atomic scale called AT1. The black line is constant except when we make a steering correction, and here you can see one in the middle of the month. That was a human adjustment. And the blue points are instead the optical clock's estimate of what the ensemble was doing, AT1. And if the ytterbium frequency is just as good as UTC NIST, then these ought to realize the same measurement. Most of the uncertainty in this comes from the fact that ytterbium does not measure the whole month. It measures just 6 days. And so there's a calculation you do with a noise model of the underlying clocks to say, well, what probably was the variance when we weren't looking? And that determines the dominating statistical uncertainty. But in any event, just this data, just these 6 days with an average uptime of about 4%, was good enough to have a measurement with about 4 parts in 10 to the 16 dominated by the dead time uncertainty. And so anyway, this is an ultra detailed glimpse of hot off the presses stuff, showing that the NIST optical clock is making official contributions, correcting the rate of international time at the 16th digit, along with all the other clocks in the world. So this goes back, I don't know, 20 years or so. And all the black dots are cesium fountains and other cesium devices. And that makes them the primary references. What's shown as in blue are the contributions from other optical clocks run around the world, which are getting more and more frequent. NIST currently has been just running them a little bit per year, but we hope to increase that. It's a difficult experiment. It requires about 5 PhDs to sit around 2 laboratories and keep a lot of equipment going. It's not yet ready to run unattended for essentially 24/7 like the cesium fountains have evolved into. But we're feeling the pressure because other labs are starting to contribute more and more. And the y-axis in this plot is just every observation's difference with respect to their primary or secondary standard and international time. And you can see because the points kind of group together and they deviate from 0 together, and that really means that they are an important contribution to fix the ensemble of commercial clocks. If left to their own devices, the commercial clocks averaged together would wander around with frequency offsets of about a part in 10 to the 15, as evidenced by the groups of these points wandering around together by about a part in 10 to the 15. Okay, the other kind of current topic is that as a result of this executive order, NIST was mandated to make available high precision source of timing that has no dependence on GPS, given GPS's weak signal level as detected on Earth. It's easily jammed. In principle, you can spoof a signal from a GNSS satellite. They sell GNSS satellite simulators, so of course you can. Our response to the executive order is manifold. A few reports were written, but we've immediately made available a service which more or less means that if you can bring a fiber to NIST, we will shove the signal down it in any format you like, effectively hosting your equipment or suggesting a signal format and providing the pulse per second and 10 megahertz or whatever primary signals you need. We also got involved in cooperative research and development agreements with several low Earth orbit satellite developers, folks investigating terrestrial beacon sort of systems. And as fast as we can, we're trying to deploy a 2-way satellite service for any agencies or industries that might want it. It has sort of a different risk profile than fiber in the ground. In any event, I wanted to at least glance on one final topic that might be of interest to this community. So WWV is the very interesting long wave station in Fort Collins. The antenna plan spans about, of order a kilometer north, and they're oriented northwest so that the beams are mostly east-west, covering the shape of the country. And WWV in most cases depends on the skywave mode to get reach out to the east and west coast. And so it's active most during the night when the ionosphere is quiet. And during the day, the ionosphere is too absorptive and the skywave doesn't propagate so well. So the radio controlled clocks you can buy online or at Walmart are sort of set to only observe during local nighttime hours. They have the best chance of getting a signal. But it turns out that mode of transmission is not so good for having a highly stable delay. There's many layers to the ionosphere. You get multipath, and it depends really on the charge content, which can depend on space weather. Instead, there's a ground wave mode of propagation, which owing to the curvature of the Earth, as you get beyond about 1,000 kilometers or 1,500 kilometers, it starts dropping off exponentially. On the other hand, if you can receive the ground mode, it's extremely stable. So NIST is supporting a cooperative research and development agreement for a sort of advanced receiver mode to try and focus in on the ground wave. So a really good antenna and a coherent receiver that can make use of the phase modulated code to dig the signal out of the noise and ask the question, how good could you really do? And could this be a mode that supports 1 microsecond sort of timing uncertainty, which would be GNSS completely independent? These are old maps showing the difference in range of local daytime versus local nighttime propagation, and shows that, and these graphs were, I mean, I think the amplitudes are still true, but the noises have gone up, especially in urban corridors. I understand that if you held a 50 ohm terminated coax around New York City, you might pick up a good fraction of a dBm. I don't know. And it really means that WWVB has a hard time at the endpoints where the major cities are. On the other hand, it was known for a long time. This is old data from, Mike, correct me, I think around, oh yeah, it says there 2003, where if you're in the ground wave, such as where this receiver was at NIST Boulder, the stability of the signal is on the order of 100 nanoseconds. The advanced receiver concept takes advantage of a software-defined radio where this is fancy enough that you might imagine shipping it with a rubidium oscillator or some relatively inexpensive atomic clock, which can allow you to ignore the daytime, or sorry, excuse me, ignore the nighttime when the sky wave is present, using the atomic clock as a holdover oscillator, and then only really process WWVB signals when the ground wave is known to be dominant. A prototype has been built. I'm showing its state about a year ago. There's been a lot of progress since, and we've also been asked to keep the progress confidential because it's proprietary. So this is the state of affairs about a year ago. It's a EDIS software-defined radio, an antenna on the roof, and NIST reference signals in the front. This was data collected from that monitoring station at NIST showing this is a point every second with no decimation. So it's showing you everything with no outlier removal or averaging or anything, and showing the same sort of 100 nanosecond stability. And the game is sort of like this on a plot of statistical noise called the Allen deviation. Essentially read that as frequency predictability as a function of averaging interval. If you can design a combination of clocks and time transfer such that the union of the curves lie below the dashed red line, it means you'll have created a composite clock and reference that can keep a microsecond forever. Here, what it means is that the orange line is a model of a rubidium clock's instability. And you should interpret this as the rubidium all on its own, once you've accounted for its frequency offset and maybe its drift, linear drift, can hold a microsecond of unpredictability to a few days, maybe 3 or 4. And that's good enough such that if you can make measurements of WWVB at high enough fidelity every day or every other day, you can correct it. And the deviation of the data observed at NIST is shown there in blue. So in fact, with just 12 hours of averaging, that's enough to usefully steer the rubidium. And it really depends how much this remains true as you get further and further away from this boulder. So that's currently under study. There's been a lot of progress in the last year, and I hope you'll be hearing about it soon. But really, that's all. I did want to reserve time for questions, so I wanted to give you just a slice. And so I'll stop here and ask if you have any questions. Thank you for your attention and invitation.
Well,
Thanks, Jeff. That was pretty impressive. I'm sure there's a lot of good questions to come. I had a couple. I have to get back to find my notes. Have we crossed the 60,000 Julian day yet?
Yes.
When was that? Just
It was a couple,
week ago.
It was a few weeks ago, and nothing at NIST broke.
All right.
You could imagine that there's about a dozen employees that have all built their systems counting in MJD, And so 60,000 was kind of our Y2K moment, and nothing broke, nothing.
All right, very good.
Uh-huh.
Whether you make it to 70,000, that we'll see, huh? That's kind of cool.
We're at 60,027 today, so.
Wow, we should have
And then-
celebrated. We should have celebrated that too. That would have been a big. No, I'm just kidding. But it is kind of funny that you have that internal. We're going to get past 60,000. I like that. That's good.
Mostly it's because I assume that everyone else is as bad a programmer as I am, but no, it turns out they're much better.
I thought it was interesting that executive order 13905 came out like 2 months after we had within a half a year after we had our 2019 anniversary of WWV. And that was when all that talk was they're going to shut down WWV and the whole bit. And so 6 months later, you get an executive order saying, well, you better have some redundancy built into the system. So that's pretty neat.
Yeah, I think this is not news to anyone, but the government's right hand and left hand often don't know what each other is doing. And I mean, there are people on this call that know the story better than I. Loran was a property of the Coast Guard, and it was subsumed by Department of Homeland Security. And I think simultaneously, Department of Homeland Security was deciding to shut it down to save of order $20 million a year. And another part of DHS was publishing a report called The Coming Storm, which highlighted GNSS vulnerability due to its ubiquity and sensitivity. And these two things were essentially happening within months of each other.
Yeah.
And it's perplexing, but well, I don't have an explanation.
Well, I'm glad they figured it out. All right. Any other questions from the gallery?
Yeah, there was, I couldn't obviously repeat it because it's quite a bit over my head, but earlier on you were talking about something I would describe as an oscillator. And you said the vibrations that you can measure or the accuracy potentially is about the width of a proton. Am I kind of sort of getting that right?
Yeah,
mean-
that's right. What I have in mind are these machined special glass or silicon objects. The glass is a 2-component glass tuned to have a 0 coefficient of thermal expansion, either at cryogenic or room temperature. And they're exquisitely designed both in shape and bonding of high reflectivity mirrors. They're oscillators because you inject light and you form a standing wave between the mirrors.
Mhm.
If you take the laser away, photons rattle around between the two mirrors for about another 50 microseconds or several 100,000 bounces. And so it's in that sense almost a realization of the Einstein clock of two mirrors that bounce a photon. And the idea is that the frequency that they resonate at is determined by the length, and the line width or instability of the length is equivalent to about the width of a proton. And you can get that because you're really averaging over a big spot, laser spot on a mirror. So the mirror is roiling in Brownian motion, but you get to average over it. And you also get to average over the fluctuations in time. They're quasi-stationary. And so that's the object I'm talking about. And of course, it means that you transfer that length, that relative length stability becomes the laser's stability. You servo the laser to be resonant with this object.
That's amazing. I guess your next goal is to be within a fraction of a proton, I suppose. I'm not sure.
The people who run the clocks just want to make them good enough such that it allows for exposing the laser to the atoms for about 1 second and having the observed noise not be limited by the local oscillator. After that point, they don't really need to make them too much better. What they might want to do is the long-term characteristics. The object is a piece of glass, and no matter how well you stabilize the temperature, there's still environmental fluctuations. And so there is some study trying to extend the stability of these, which is not a fundamental problem. It's sort of a material science problem. Yep.
On the one picture of the lasers where we had the definitive colors, and you had the frequency listed for the yellow laser. When I was looking at that, was that like 1,000,000 times more frequency than the cesium? Is that about right?
Well, it's about 100,000 in general. But yes.
100,000.
Well, I mean, let's see. The cesium frequency is about 10 gigahertz, and these are all 500 terahertz or so. So like 10 to the 14. So it's, well, maybe, I'm sorry, maybe that's 50,000. Yeah.
But still, that's the precision you'll gain by going to the optical.
Well, that's potentially what you'll gain if everything were equal, and it's not. So it turns out that take magnetic field effects. For a microwave clock and an optical clock, the magnetic sensitivity is about the same. And so you get to divide by a bigger denominator in the optical clock and you win big. That photo had no magnetic shielding because we don't need it. On the other hand, it turns out that the Stark effect from black body radiation, infrared light, turns out to be about the same. Relative motion, Doppler effects turn out to be the same, and they don't care about the absolute frequency. It's a relative motional effect. So it turns out there are some effects where you get a huge benefit from having the bigger denominator in frequency, but then you lose it all in things like motion and the black body effect. So you don't win by the straight 50,000. What the big print gives, the fine print takes away, as usual.
And that's the constant battle of that's your job, is to battle that trade-off. That's kind of fun. That's neat. Anybody else have any questions for Jeff?
Yeah, I do. I'm wondering how close the time over fiber product is to being generally available.
We have of order 4 customers now, both from the Gaithersburg site and the Boulder site. And it's in our service catalog. The service catalog item will generate a request to have a chat with our division chief, Liz Donnelly, and Judah Levine. He'll want to interview about just what performance you're looking for, and they'll quote you a cost. But the significant cost is perhaps going out and getting the least fiber in. And if you really need something at the nanosecond level, you need the equivalent of a dark wavelength or a dark fiber without any telecom routing. And
yeah, you could carry it as a forward wave on any kind of DWDM system. That's fine. My application is not the accuracy so much as diffusing some of the single source risk, and that's really a much higher concern for me. And honestly, traceability, auditing the traceability, having the space segment and the ground segment of GPS in the middle is fine. But I work for a very large bank, and we kind of care about traceability for obvious reasons. You attest things happening at a certain time in court on like a regular basis. So we're in the process of re-architecting our NTP stuff, and we are very close to Gaithersburg, which will probably give you an idea of who we are. And getting fiber from Gaithersburg to Equinix and Ashburn should be straightforward and not terribly expensive. So I may put that on my action items list.
that's great. And yeah, I appreciate that need for not ultimate accuracy. Just to calibrate, I think we have a customer who has leased essentially routed Ethernet, and is running just layer 2 PTP. So we are essentially co-hosting his equipment just as they set it up in our lab, and we don't touch it beyond giving them the pulse per second and 10 megahertz. And then it goes to their layer 2 network. And across the country, he's seeing noise bounded at 5 microseconds, 10 microseconds or so, which is not terrible. And he owns everything in the path, and that's important for being able to stand
Yes,
up in federal
well,
court.
to put that in context, I have trouble explaining, I have to explain over and over. I don't have trouble explaining it because I have it down to a science at this point. But the actual, we only log to a resolution of 1 second. Why on earth do we need, guys, you want a high likelihood of your event ending up in the right bucket, right? So, how about we chase, 100 microseconds or so? And I think we're probably fine with that in our application. But really, that's good to hear that you're open to that sort of thing, and that it's. I think that there are a lot of folks who, once you drill down into it, have that use case in mind. So the other question is, where do the time sources converge, if any? Am I complete to an independent cluster of CCM clocks with this versus WWV B versus GPS? Because I don't want to get redundant paths only to have it do this, and I'm conscious of the Byzantine generals problem.
Okay, well, we can talk in as much detail as you like, but generally, if you subscribe to the service at Boulder, you get UTC NIST out of a distribution amplifier, and you will be told that UTC NIST is prone to certain failure modes, will have a certain time to fix and time to inform you that there's a problem, but it is the signal that we use to transmit to Europe, that we use in the lab, and it is the ensemble clock of up to 14 masers and 6 or so cesium beams. In
Yep.
Gaithersburg, on the other hand, we only have 2 5071 cesium beams in a primary secondary mode, and whose time offset we set with GNSS dependence, not directly. We don't depend on the GPS time, but we use GPS in common view to Boulder.
Yeah, I'm familiar with common view. That kind of blew my mind when it was first explained to me. So,
and the radio station is a bit better. There are 5 cesiums run as an ensemble, but also whose absolute offset is known by GNSS common view. We are looking at upgrading our techniques for calibrating such that we don't depend on common view either. That essentially means putting 2-way satellite antenna at all the sites. And as budget allows, that's something we're looking into, which would remove GNSS even availability as a dependency. But a subscriber to the service will get a long series of lectures and disclaimers about what you're getting. And there's an inevitable trade-off. If you get closer to the primary reference, the failure modes increase, but the precision also increases. And if what you want is instead a single clock that's referenced, which will have a different sort of failure mode, but holdover against the primary failure, that's something that can be designed.
Yeah, my primary concern is something that you would consider abysmally poor accuracy, but extremely high reliability. So that's very cool. Thank you.
Rob, I hope you can figure it out, and I hope it doesn't cost an arm and a leg to get connected to Gaithersburg.
Probably not that bad, actually. And, we already have contracts with all the fiber folks and everything.
All right, good luck. Any other questions? We're getting on to about 7:15. I think there's another Sweet 16 game starting up here soon, so we have to be careful. Go ahead.
I'll give a shot at attempting not to sound really stupid, only partially stupid. Can you talk maybe or pontificate a little to the future? How do you explain to common people why you need to have ever increasing accuracies And what do you think you'll be doing 10 years from now?
Yeah, fantastic question. I left out the kind of applications slide, I suppose. It's always been the case that a better clock has led to better applications, new sensors, and fundamental science. And I'll give some examples for all those. As was pointed out in Dave's description of the tour, every meter of elevation above Earth's surface means time, however you measurement, ticks differently in the 16th decimal place. So it really runs faster at your head than it does at your feet. And it means that clocks could be turned into the accurate elevation machines. And not just elevation, but what it's really measuring is gravitational potential from any source. So for example, you might be able to see over 100 square kilometer sort of regions, the flow of underground water, adding weight seasonally. And so there are satellites that if they flew these clocks, could turn into what's being termed relativistic geodesy instruments. You won't, I don't think you'll be able to find oil deposits this way. The structures are too small, but large structures you'll see, and maybe uniquely so. GPS is not stable enough to see elevation at the 5 centimeter level or so. It's just not possible. And yet the clocks that have 10 to the minus 18 frequency accuracy can resolve 1 centimeter changes. And if you look online at Juni's work at the University of Colorado, just across the street from NIST, he's worked it out so that one of these atom traps can consider 2 populations of atoms in the same vacuum system, but spread over a vertical height of just a few millimeters. And he can see the difference in ticking rate in the 20th decimal place, where of course the rest of the systematics are common and unknown. So it wouldn't feature as a clock, but as a gravimeter, he's got it. So that's one application. That's a completely new technological application. There are several others that can be improved. Communications, in terms of crowding in close to a carrier, you could always use higher coherence in your local oscillators. Very long baseline interferometry and Doppler radar of slow moving objects like, say, balloons in the sky. Anybody? It turns out that you need quiet oscillators close to carrier. And all the good oscillators, cryogenically cooled, whatever, are very quiet, far from carrier. But once you're close to carrier, you're deep in the flicker Brownian motion kind of world. And that's exactly the point that you want to jump off the material and onto the atom. And I think those are sort of expensive but important possible applications.
Cool.
There's also fundamental science. So all these assertions that I made that are testable are being rigorously tested. And for example, a fifth fundamental force or transient dark matter, if it has coupling that's stronger for one atom than another, then you might see it as the Earth moves through the galaxy, traverses hypothetical scalar light dark matter. You might see it as one clock speeds up while the other one doesn't, and then it relaxes. Well, that might be because we've just transited through a dark matter field. So of course that's speculative, and there's 1,000 models, all speculative. And so right now the clocks just put limits on those models. They sort of disprove those models. But that's an important method of progress where I'm sure you're aware fundamental physics is sort of stymied at the moment with outstanding puzzles and no clear way forward. For example, with the lack of supersymmetric particles showing up, the Higgs boson is in a weird energy. We know the universe is full of dark matter, but nobody knows what it is. And the comparison between clocks is the sort of one tabletop apparatus that has sensitivity to it. So there may be zero signal for 20 years, but only after 20 years of improved development, maybe we'll see something. So, I mean, it's in that spirit.
Merry Christmas.
Thank you.
That is fun. Sounds like some good sci-fi coming up from all of that too. That's amazing. Well, Jeff, I can't thank you enough for taking the time out to visit with us and to give a great presentation. Definitely a lot over my head, but at the same time, you did a great job explaining it. It made a lot of sense. So thank you so much.
All right. Well, thank you all. I appreciate the invitation and the club as well. It was fantastic about the anniversary event, which I'm afraid I had to miss, but I'm glad I got a summary here. And let's stay in touch.
You bet. Thank you so much, Jeff.
All right. Take care, all.
Thank you, Jeff.
Bye.
Thank you very much.
So everybody, thank you so much for being here this evening. And I think I got that taped. So if I can get that available to people that want to review an incredible presentation, that was really neat. Mike, do you want to add anything to the discussion since you're unmuted there?
No, I'm fine.
Okay,
Well, actually, one thing is if Jeff already logged off, I believe.
I think he snuck off. Yep.
Maybe you gentlemen, and maybe myself, we should convince Jeff to become a ham.
I was gonna ask him, but I decided
Yeah.
not to.
He could be the
Yeah, but,
ultimate ham radio operator. He could be.
Like he's got free time to think about ham radio, right?
But
Yeah, but he'd kill us all on a frequency measuring test, I have a feeling. So.
Yeah, I think he could do a pretty good job. I would be afraid that I would wake up in the middle of the night and one of these problems he's thinking about, it would just get stuck in my head. I'd never get any sleep. You know, you sit there and you go, gosh darn this thing at 4 a.m, you know. It always keeps me up all day long. Some thought going. I can't imagine what's going on in his head. That's really cool.
Yeah, I think he will become a ham at some point, and maybe keep the bug in his ear.
Yeah, that's great.
He's
very good.
super talented.
Excellent.
Okay, thank you.
Well, guys, I'm going to go watch some basketball. Have a great evening, and we'll be in touch. I don't have anything planned for that April 27th meeting yet, but we'll find something to have. That was a pretty good conversation tonight. I must say that was a lot of fun.
Yeah, thank you for setting that up.
What a
You bet.
fantastic
Thanks.
presentation. Thanks.
Yeah.
You did.
Absolutely
guys.
wonderful.
Have a great evening and 7-3.
Cheers, gents.
73 all.
Cheers.
Cheers.
Good night.
It did.
A few of us left. Oh, you're muted, Darren. I can't hear you.
Sorry, I am so sorry. I swore
was
the meeting was
surprised.
at 7.
Well, it was at 7 o'clock. 7 o'clock was the FMT. 6 o'clock is what we're doing. 6 o'clock because on the East Coast that's 8 o'clock. You know, we'd hate
Yeah.
to start later than that. So, Darren, how you feeling
I
after
just-
your last treatment?
You know, so. I mean,
Yeah.
it didn't hit me as bad as last time, but it's still hitting me some.
Okay.